can see your screen.
See one?
Full screen, yes. Please
Perfect.
go ahead. Thanks.
Thank you very much for inviting me to contribute to this meeting. My talk is centered on the physics of a top quark that interacts strongly with new dynamics beyond the standard model, for which, even if the new physics states are out of direct reach, one expects large non-standard effects in the form of effective for top contact interactions. So let me start by recalling that while the strongly interacting top quark is usually associated with compositeness, we know basically since its discovery at Tevatron that the top is not a composite like, for instance, the proton is. So for a composite fermionic proton, one finds a non-trivial substructure when probed with energies of the order of its mass. In other words, for the proton, one finds that the composite scale, which I define in this talk as m star, is of order m proton. Now, this, sorry. Now, since this is not the case for the top quark, I like the notation that what we are actually studying today concerning the top quark is its degree of chiral effective compositeness. So this is just because of chiral symmetry, under which left and right components transform differently, provides a simple rationale of why top mass can be much lighter than its composite scale. So of course, this hierarchy means that we can study a strongly interacting top by means of an effective field theory. So Georgia and company, already in the 90s, identified the genuine higher dimensional operators associated with this by now standard type of compositeness. So a leading order in expansion in fields and derivatives, there are two qualitatively different types of operators, 4 fermion operators and operators with a fermion bilinear and 3 derivatives. So note that I'm normalizing the operators with the compositeness scale, m star. At this scale, the HEFT breaks down, new resonances need to be incorporated, or just the top melts into more fundamental degrees of freedom. In addition, note also that I'm treating separately right-handed and left-handed top compositeness. Now, these two classes of operators are different because of their maximal size. The coefficients of the 4 top operators scale with a coupling squared, which I define here as G star. Therefore, their effects can get comparatively large within the effective field theory if the underlying dynamics is strongly coupled. That is, if G star is larger than 1 up to roughly 4 pi. So these operators, therefore, encode the most genuine consequence of top compositeness, which we can probe when scattering the top against another top to produce another 2 tops in the final state, a 4 top scattering that grows with the energy of the process. As I will show shortly, only recently the LHC has managed to probe such 4 top production at an interesting level. Let me note in passing that there is just one other type of theoretically consistent effective compositeness, providing as well a natural separation between the particle's mass and its compositeness scale, that in this case is associated with a non-linearly realized supersymmetry. This is why the name of Costino compositeness. So the leading genuine effects are encoded in dimension 8 for fermion operators with 2 extra derivatives with respect to the standard compositeness, which lead to amplitudes that grow like a higher power of the energy. And in addition, its coefficients are theoretically constrained to be positive if their UV completion is to be unitary, local, and capsule. Now, coming back to standard compositeness, the other class of operators is not enhanced at strong coupling. And most importantly, physical processes where these operators enter necessarily involve other standard model particles, something that can be simply shown by using the equations of motion. So one then finds that these operators are in fact equivalent to operators with the Higgs boson, which modify the top couplings to the W and the Z, or with another fermion, with the Higgs and the other chiral at the top, leading to a dipole coupling, or an operator that modifies the top coupling to the Higgs. So importantly, all these operators are suppressed by a small standard model coupling, and therefore give rise a priori to smaller effects than the 4 top operator. In addition, the interpretation in terms of top compositeness is complicated by the fact that we have other fields. So take, for instance, this 4 fermion operator. If the non-top fermion F were as composite as the top is, the coefficient of the mixed Fermion operator would be enhanced by G star squared instead of just gauge coupling squared. In this regard, it's very important to understand the power counting, that is the expected size of the operators associated with the theory that we are trying to study. Now, the model dependence of this class of operators becomes manifest when we contrast them with the motivations for a strongly interacting top. So certainly it's interesting to consider the idea of top compositeness on its own in our continued search for the inner structure of the particles currently viewed as fundamental. In addition, in the past, top compositeness has been considered in the context of an explanation for the large hierarchies in the masses of the standard model fermions. However, let me note that none of these ideas single out per se the top quark, nor the fact that we should find its composite at TV energies. So from my point of view, the best motivation for this is the origin of the letter V scale, something that can be intuitively understood just by the fact that since the top is the heaviest, it is the one most sensitive to whatever dynamics solves the letter V hierarchy problem. Now, this is in fact explicitly verified in one of the most interesting BSM scenarios for the letter weak symmetry breaking, which is the idea that the Higgs is also composite. So very briefly, there is neutron dynamics that gives rise to the Higgs field at the PV scale in a similar fashion as QCD gives rise to the pions. So this means that the Higgs arises in fact as a Goldstone boson whose potential in first approximation vanishes. So this provides a rationale why the Higgs is lighter than the composite scale. Now, this scenario is in fact viable, meaning the electroweak symmetry is eventually broken thanks to the top quark. Since the Higgs must eventually couple to standard model fermions, in particular the top, and to the electroweak gauge bosons, these couplings are responsible for generating the Higgs potential. Importantly, the Higgs mass squared turns out negative because the top provides the largest contribution. In turn, top compositeness is a natural consequence. Each top chirality must couple to the strong dynamics with strength large enough to generate a large top Yukawa. Now, this scenario motivates them to consider together, as well as to compare, top and Higgs compositeness, which of course has consequences on the expected size of the operators we saw are associated with a strongly interacting top. So to be concrete, and also because it's favored by experimental consistency as well as fine-tuning considerations, I will focus on, from now on a maximally strongly coupled right-handed top. Okay? That means that the top right is effectively composite at the scale m star, and with operators determined by the coupling G star. So here I present a summary of the most important operators, their expected size in terms of m star and G star, as well as their current constraints. So I will not go through the list. The main message is that different operators are sensitive to different combinations of the compositeness scale and coupling. And in addition, all the direct bounds, which come from the LHC, are in fact quite weak. In particular, if we compare with Higgs and electroweak position measurements. So this is with the exception of photo production, which is shown by the orange shaded region in this plot, already with 36 inverse femtobarns of data, provides a comparable to sigma sensitivity in the scale coupling parameter space than precision Higgs data, shown by the blue shaded region and encoded in the genuine 4 Higgs operator shown here. So let me recall at this point the obvious caveat with interpretation of this plot, which is that there are order 1 numbers all over the place, from the order 1 uncertainty in the Wilson coefficients when expressed just in terms of m star and G star alone. So this plot should then be taken just as a guide towards which operators observables are most interesting to probe which parts of the parameter space. The conclusion is nevertheless robust. Tests of the 4 top operator are one of the most interesting experimental targets, motivating their study at the next rounds of the LHC as well as future colliders. So before presenting our work on 4 tops at future colliders, let me note that already now the experimental situation is, in my opinion, very interesting. This is because run-to LHC data shows a pattern of mild but coherent excesses in final states with multi-leptons plus jets. So here I show you our summary, which includes analysis from both ATLAS and CMS of four-top production, as well as top pair production in association with Higgs, a W or Z. Most noticeable is that measurements of the TTW cross-section are, even if with large errors, systematically 2 sigma above the standard model prediction, which has been computed, by the way, at full NLO. So this has sparked quite a significant theoretical activity, mainly devoted to the improvement of the standard model prediction for TTW production. But still, no resolution has been provided, nor from the theory nor the experimental sides. So in light of this, we decided to briefly explore it in the context of new physics in top and Higgs sector. In particular, we reinterpreted this particular four-top analysis of CMS performed in the same sign dilepton channel, basically because it provided the necessary information for us to validate our simulations. Now, our analysis can certainly be improved. We only included what would be the leading new physics effects in the form of 2-dimensional 6 operators, a 4-top right contact operator, and a Higgs current top current operator, which changes the coupling of the right-handed top to the Z, and thus leads to deviations from the standard model prediction, both in TTZ production as well as TTW production. For this case, via TW scattering that grows as well with the energy of the process. So let me remark that both TTW and TTZ are very important in searches for top production, since they constitute the main irreducible backgrounds in the same sign dilepton channel. So we performed joint fit to the 4-top signal region, as well as the TTW and TTZ control regions shown here, with the pre-fit number of events, experimental data, and including the best fit point for the BSM contributions. The summary is shown in this plot with 1, 2, and 3 sigma contours in the plane of Wilson coefficients. The best fit point suggests a non-vanishing value of CHT with a 2 sigma preference, and even if with less confidence, a non-vanishing value of the 4-top operator. So 2 interesting things came out of this little exercise. So 1, the goodness of the fit is at the same level as a simpler yet less motivated rescaling of the signal strengths, shown here. And the size of the resulting Wilson coefficients is sensible, by which I mean that they point towards a scale, m star over g star, in the ballpark of what is still experimentally allowed from other 4-top production measurements, as well as Higgs coupling measurements. So in any case, I think this is at least an additional motivation to explore the physics of a strongly interactive top quark at future colliders, which is in fact the bulk of our work. So first, we studied the sensitivity of a future circular hadron machine at 100 TeV center of mass energy. In this case, the strategy is clear. So take advantage of the high collision energies, along with the fact that the TT scattering mediated by this 4-top contact interaction grows with energy to enhance the signal for the production. So some important points concerning our analysis are the following. So we thoroughly analyzed both the same sign dilepton as well as the trilepton channels. The main irreducible backgrounds in these channels are the standard model for top production, as well as top pair production in association with W, Z, and Higgs. So there is, of course, a significant enhancement of the standard model for top production cross-section with respect to the LHC. But this is, in fact, larger than the corresponding enhancement on the main backgrounds. For instance, shown here, the number for TTW production. Finally, we estimated or validated the main reducible backgrounds, which are fake leptons as well as charge flips, using LHC data on top pair production plus jets. So partly following previous analysis. So we have found that the signal sensitivities in the same sign leptons and 3 leptons are similar after exploiting the hardness of the signal bands. So for instance, in the same sign channel, we applied, after baseline selection, strong cuts on the PT of the leading lepton, as well as on the scalar sum of the transverse momenta. Since as shown in these plots, this is the region of kinematical space where the signal is most enhanced, while remaining with a good signal to background ratio. So in addition, we have checked the dependence of the signal sensitivity on the systematic uncertainties of the main backgrounds, 4 tops and PTW, as well as a function of the EFT cutoff. And this is the result. So taking again the Wilson coefficient of the 4 top operator to be set by the strong coupling squared, we find to sigma sensitivity to a compositeness scale over coupling of 6.5 TeV, which is an impressive, in my opinion, order of magnitude stronger than at the LHC. So in addition, again taking exactly the same value for the Wilson coefficient of the 4 Higgs operator that enters Higgs position data, we find that 4 top production provides a larger coverage of the M star G star plane, even if this 4.2 TeV from the Higgs has been derived taking into account not only the hadron-hadron, but also the electron-positron phase of the FCC. Finally, so let me discuss our findings concerning future lepton colliders. As I will show shortly, these are in some sense surprisingly impressive, since it is clearly not feasible to probe the 4 top contact interaction directly at lepton colliders. So, however, it turns out that it leads to a large contribution via renormalization group evolution to 2 lepton 2 top operators, which can be certainly tested in top pair production. So here I show you some of the details, which are important not only because of the obvious fact that the RGE contribution is logarithmically enhanced, but because of the somewhat large coefficient that comes with the loop suppression. Besides, one can expect additional 3-level UV contributions to the same 2 lepton 2 top operators, but these arise from that class of operators I discussed at the beginning of my talk that are not enhanced at strong coupling. So this then means that for strongly coupled dynamics, that is G star larger than 1, the RG term dominates, which allow us to probe directly the 4 top operator. This is again the result of the particular power counting of the operators associated with strongly interacting top quark. So, certainly, there are many other PSM effects that end up top pair production at lepton colliders, in addition to the 4 fermion contact interactions. In particular, modified couplings to the Z and dipole interactions. However, first, they have a different behavior with energy and beam polarization, both of which can be adjusted. And second, as I've been discussing, they scale differently with the new physics coupling. So in particular, the 4 fermion operators dominate at the highest collision energies and for large couplings. So these simple facts are behind the differences in the scale coupling sensitivity when we compare a lepton collider such as ILC running up to 1 TeV with click running up to 3 TeV, as shown in this plot. So while the importance of top dipole and top Z couplings is similar at both colliders and somewhat limited, top pair production via contact interactions would be able to reach large composite scales, in particular in the strongly interacting case, as shown by the orange. So the difference between ILC and click is simply understood as the relative enhancement of the sensitivity with collision energy, as well as the square root of the luminosity, since for both colliders, the errors are statistically dominated. By the way, let me note that we produced this plot reinterpreting the results of a very comprehensive study of top quark HEFT effects and lepton colliders by these authors. The summary is that we find that the indirect effect of the four-top operator leads to the strongest sensitivity to the idea of a strongly interacting top. So in fact, it is so powerful that once again, with the caveat of order 1 factors, probing the four-top operator at click would give us access to a larger portion of parameter space than Higgs position probes. Particularly, we find 2 sigma sensitivity to a composite scale over coupling of 7.7 dB, which is even slightly stronger than at the FCC. And finally, if we were to establish that errors in topper production would be statistically dominated as well at a muon collider of 10 TeV center of mass energy with an integrated luminosity of 10 inverse attobarns, we would find an even more impressive reach of 18 dB. So with this, I reach my conclusions. So I believe a strongly interacting top quark is a very interesting target for high energy colliders. Current LXC sensitivity from 4 top production is already competitive with Higgs measurements in the context of Higgs and top compositeness. Plus, there might be already something interesting in the data. Future colliders, in particular those running at the highest center of mass energies, would allow very powerful tests of a strongly interacting top quark, reaching values of the compositeness scale over coupling, which determine the size of the 4-top contact interaction that approach the 10 TeV mark. Another way to phrase this result is that we will be able to explore levels of electroweak scale fine-tuning below the per mil level, which is 100 times below that of the LHC, and I think unprecedented in the realm of particle physics. Thank you very much.
Thank you, Javi. Questions from the conference room?
Questions? I don't see any at the moment.
Anyone online? Let me ask maybe in the meantime. So you would talked about TT-bar production at E plus E minus colliders or mu plus mu minus, but didn't mention TT-bar production at hadron colliders. Is that the sensitivity is not competitive there?
Well, we did this exercise. Thanks for the question. We did this exercise for the LHC. It turns out that there is not TT-bar production is not competitive.
Mm-hmm. And also seeing the kind of scale that you constrain at the LHC, something like 700, 800 GeV. I mean, would it be interesting to look for resonances in TT-bar, or is that not competitive either? Well,
so as I was saying, the conclusion from LHC is that it would not be competitive. In this sense, you better have you would have better chances to go and look for resonances in TT-bar associated production with these resonances.
Okay, TT-bar associated production.
But that doesn't mean that TT-bar wouldn't be interesting per se. Okay, it's a good question.
Okay, Alejo has a question.
Yes, thanks, Gautier, thanks, Javi, for the nice talk. My question is to get an idea of the validity of your EFT of the cutoff, which is approximately the maximal square root of S of the events at FCCHH that you get your sensitivity from.
Yeah, so we checked. Let me go back to the slides. This is slides, yes?
Yep.
Yep.
So this is what we were trying to do. Of course, at the lepton colliders is
Yes, the center of
greater,
mass of the leptons. In that case, very clear. But in
but
the FCC is not a.
yeah, so we checked how the bounds would on the size of the four top operator would change. We cut the maximum varying mass of a hardest TT bar pair, because that in some sense it's a measure of the regime of validity of the EFT. Okay. So, and we can see that already for somewhat large couplings, Z star over or equal 3, we saturate the bound that I was quoting. Yes. So
Okay.
of course, this means that for smaller couplings, one would enter the regime where one is likely to produce the resonance on shell. And therefore, we would have to take these events out of our EFT analysis. Yes? This is basically this plot.
Okay, thanks. Yeah, I hadn't seen it before, sorry.
Thanks for the question.
Is there any last question from the room or online?
Maybe I have a question.
Go ahead.
Just a curiosity. So you focus on the right-handed top compositeness. I guess since the left-handed top, you can even test via bottom. Or also for
yeah, that's right. That's right. So we focused on this case because of theoretical bias. But of course,
yes.
So the bounds and the coverage would be the same if you change top right for Q left, yes, and you assume the same power counting. Okay. Now it's interesting that you mentioned this because with this power counting for a strongly interacting top right, turns out that, for instance, at lepton colliders, there is an interesting coverage of the small G star region through BB bar production. Okay, so that's interesting. Now, at the LHC, of course, you could go to, yes, you could produce botons or go directly to botons. I'm not certain we actually check this. I don't think so, but I would say, yeah, I'm not sure it would be if it would be stronger, in fact, because you are. Well, it depends on where the process that you're thinking.
Yeah.
It's either PDF suppressed if you pick the buttons hard. Yeah, it's an interesting question. Thanks.
Okay, thank you.
Great, thanks again, Javi. So sorry that we went a little bit over time. We now have a coffee break.